Hey everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we are diving into some fascinating AI research. We'll be looking at a paper called Vision as LoRA, or VoRA for short. The core idea here is pretty neat. Instead of bolting on a separate vision component to a large language model to make it multimodal, VoRA actually integrates vision-specific LoRA layers directly into the LLM itself. This means the vision parts essentially become part of the language model, which simplifies the architecture quite a bit and cuts down on computational overhead. Right, so building on that idea, what we're looking at here is actually the GitHub repository for VoRA. It's great because the researchers have shared everything publicly. You can see the code structure. The README file there has the abstract, installation steps, details on the datasets they used for pre-training, like DataComp1B and GLDV2, and even links to the model weights. So, yeah, full transparency, which is always good to see, helps others really understand and potentially use this VoRA approach. Okay, so this figure really illustrates the difference I was talking about. On the left, you see the typical way multimodal models are built. They have a separate vision encoder, like a VIT, then a connector piece, and finally the large language model. It's quite modular. But then on the right, that's VoRA. See how much simpler it looks? The image patches go through an embedding layer and then straight into the LLM itself. The key thing is those LoRA layers, marked with that little eye icon, are inside the LLM. They handle the vision part directly within the language model structure, getting rid of the need for that separate vision encoder and connector. It really visually highlights that streamlined approach. Okay, so going a bit deeper now, this figure breaks down how VoRA works during pre-training versus inference. On the left, during pre-training, you can see that the main LLM blocks, marked with the snowflake, are kept frozen. Only the LoRA layers, with the little flame icon, and that initial visual embedding layer are actually trained. They also show this blockwise distillation step, using a pre-trained V to help guide the training. Then, importantly, on the right, for inference, those LoRA layers get merged right into the LLM blocks. See, they're gone as separate things. This means, well, there's basically no extra computational cost or memory overhead during inference compared to the base LLM, which is a big plus. Right, so remember how I mentioned they freeze the LLM during pre-training? Well, this figure really shows why that's important. It's plotting the language modeling loss during training. Look at that purple line. That's what happens when they tried training the entire LLM with the new vision data. See that huge spike? The loss just collapses. Basically, the training becomes unstable. But then, look at the orange and red lines. Those represent training using the VoRA approach, freezing the main LLM and only training the LoRA layers. Much smoother, right? The training is stable. The red line, which uses that blockwise distillation and the bidirectional attention we talked about, actually performs slightly better, achieving a lower loss overall. So this really backs up their design choice. Okay, so building on that loss comparison, this figure digs into the data efficiency of those different approaches. It's plotting the relative number of training steps needed to hit certain loss targets. The orange line is the baseline, just plain LoRA with causal attention. Now, look at the green and red lines again. The green line adds that bidirectional attention we talked about, and you can see it needs fewer steps. It's more efficient than the baseline. But the red line, that's the full VoRA setup with bidirectional attention and blockwise distillation, is significantly faster. For example, to reach a loss of 1.1, it only needs about 65% of the training steps compared to the baseline. So, yeah, that combination really speeds things up. And wrapping things up today, VoRA really seems to offer a stable and, well, significantly more data-efficient way to adapt these large, pre-trained vision models. Combining those LoRA ideas with bidirectional attention and that blockwise distillation really pays off. This is important because it could make fine-tuning powerful vision models much more practical, maybe even for those without massive compute budgets. Well, that's all the time we have. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.